Okay, I'm just going to say a few words then, just to open this evening. So thank you everyone for joining us. Obviously a massive thank you to Wiem for being with us. A few words, like I say, a bit of background and a bit of a call for help. For those of you that don't know me, my name's Barry Cranford. I'm the founder of the London Java community. So I'm not a developer myself. I run a tech recruitment company called RecWorks. And here at RecWorks, we've been on a bit of a mission for the last 12 years to prove that recruitment can be a force for good in the tech industry beyond just getting people jobs. And that's specifically around learning, career development, mentoring, that kind of thing. So what we try and do is create groups and platforms where we connect the people that want to share with those that want to learn. So that's done on a group basis like this evening and through communities like the London Java community. And also on a one-to-one level. The one-to-ones usually happen through our Meet a Mentor community. So you can always have a look at meetamentor.co.uk if you want to know more about that. As for what I'm looking for help with, every second Friday, we hold a Lightning Talks event as part of an Aspiring Speakers initiative that we run. So this Friday, we were short, I think 4 at the beginning of yesterday, and now we're just looking for 1 more person. So if anybody is keen to volunteer, then please do let me know. We have any experience, so inexperienced all the way through to experienced speakers. It's all powered through recruitment, so revenue that we generate through recruitment. So if you are looking to hire or you're looking for a role, then please do bear RecWorks in mind. Anyway, on to this evening. So we're lucky to be joined with Wiem Zine Elabidine, who is a software engineer at MOIA Hamburg. So she writes Scala and contributes to a Scala open source project called ZIO. And she's very enthusiastic about functional programming. So Wiem, when you're ready.
Thank you for the introduction. And thanks to all the organizers for inviting me. Okay, I will share my screen just. Trying to look which. Can you see my screen? Nice. All right. Welcome to this talk, Concurrency on the JVM using Scala. I know it is a Java meetup, but I think what I'm going to talk about would be quite familiar to you. And it would be interesting to see how we are dealing with concurrency using Scala, a different programming language, but is running on the JVM. So first of all, I'm going to talk about the difference between parallelism and concurrency. Then I will present some data types that we can describe parallel computations using them, and which kind of challenges that we can face in our concurrent programs. Then we will try to solve these problems. There would be different solutions, but I am going to focus more about the solution built on a Scala library called ZIO. It is important to distinguish between the difference between parallelism and concurrency. They are quite similar, but they are different. Parallelism depends to the hardware. It's using the capability of the hardware, you can achieve parallelism. So you can have different tasks running simultaneously. And concurrency is the ability to run different tasks out of order without affecting the final outcome. Let's see an example. For example, we have a machine with 4 cores. we can achieve parallelism. We can have 4 tasks running in parallel. And also we can have concurrency. So we have concurrent tasks here, and they are running out of order. This is true, but we can also have, we can say this program is parallel because we also have, at some point in time, they are running all together. So this is, it's fine to say we have parallel tasks, even in a concurrent program. But also when we have more than 4 tasks, we can execute them in 4 cores. We can run them, and these tasks will interleave each other's. And in case if we have these tasks running in a single core, we cannot achieve parallel programs. We cannot have parallel programs in a single core, but we can have concurrent programs in which these tasks will interleave each other's. For example, this task will be run, and then the second, it will be suspended. The second task will execute the first instructions, and then it will be suspended. The other task will be resumed, etc. This interleaving between these tasks, call it concurrency also. This is why sometimes in different programming languages, like in JavaScript, we can have concurrent programs and asynchronous programs because of this, even they are running on a single core. So now let's see how could we describe parallel computations. So the first data type that we would think of is thread, and a thread would have a single method run. This is how we create our threads, and this has 2 instructions. And this thread is it is a linear flow of execution managed by a scheduler. The scheduler is a part of the operating system that decides which process runs at a certain point in time, and the time each thread will take, it's non-deterministic. This is why the out-of-order execution that we have in concurrent programs. So in case when we execute 2 tasks, for example, this, when we start the first task and the second task, and we run the program, we will see different results. For example, here we see that the first instruction of the first task starts, and then the second task interleaves this computation, and then the task 1 back resumes and completes its second instruction, and finally the second task will complete its instruction. When you run the program again, you will see another result, another order of execution. So all of this called execution order, which depends to the number of instructions and the number of threads. So here, for n instructions and t thread, there are n times t steps. There is a context switch between the t threads on each step. This equation was taken from Clean Code book by Uncle Bob, and now in our example, if we want to just to have an idea the possible execution paths that we will have 6 possible results, possible order. So now when we think that, oh, okay, we use threads to have concurrent computations, but it is quite tricky because one thread matched to one operating system thread, it is an expensive operation because imagine if, for example, we can check the available processors that we have in our machine. And imagine if we have, for example, 4 and we have 10 threads. This will like the 4 threads will be executing, but the other 6 threads the other threads will be suspended. And this is really expensive operation. This is why it is better to use thread pool. And the thread pool keeps storing all the tasks that you have submitted to the executor service, and all threads, the workers, will take the tasks and execute them and then wait to the next task to be executed, etc. Now it's like we have the power to define or to control how many threads we want to use, how many workers, and each worker can execute different tasks and not only one task. And this also will provide many more interleaving between the tasks, and it's fine. So the thread pool helps us to save resources. And for example, when we create this thread pool with fixed thread, this enables us to control the number of the created threads. And here we will have 2 workers that will execute 1,000 concurrent tasks. And there are different types of thread pools. It depends to the use case. In Scala, we have a data type called future. It has a type parameter, which would be the type of the value that will be available in the future. So Scala Future is a data type that represents a value that will be available in the future. And it is like, for the same example, it is simple when you see it. Just future has an apply function, so you can call future like you construct this with your instructions, and then you run this task, each like 1,000 tasks. But when you try to run this, it will not compile, because you have to specify which execution context that this future will be executed. And the suggestion here is to import the execution context implicit global. The global execution context, when you import it, it will implicitly will be used in this future, and this will take all the available processors that the available number of the cores that you can use, or the threads that you can use. For example, you have 4 available ones, so you will have 4 workers, and they will execute each tasks. In order to control this, you can create your own execution context using from executor, and you can specify which kind of thread pool you would like to use. If you define this as an implicit val, it is all right, and you shouldn't import that global execution context. Otherwise, it will not compile, because ambiguous execution context. And otherwise, if you don't want to put it as implicit, you can call it explicitly here as a second argument in the future here. The good and the nice thing in future that you can use them as a value. You can pass them around functions, and you can have a computation that returns future. So Here, for example, it is using flat map and map, we can achieve composability, because when we have a future and you call flat map, you can access to the produced value of that future, the first future, and use it to compute the next future. And map, it will do some computation using the result of the given future. And in general, in Scala, we have like the data types, the containers have flat map and map, and this enables us to use the syntax sugar for comprehension. It is the same. It is as you prefer, if you would like to use it as like this, or you can use it like this. And here it's like, here you take the result of delete user, and flat map you take the result of picture, and then here yield map, and do that this computation. And the future might succeed with a Boolean, but also it might fail. It can fail with throwable. In order to handle the error, you can call recover. So you see how it is composable. You can call recover, and here would be the kind of exception that you get, and what you want to do how would you like to handle this exception. In this case, we always will succeed, but with false here. And if you would like to get out the value from the future, and if you are you would like to, at that point in time, you would like to check whether the value is ready or not, you can call dot value. If the value of the future, the computation is ready, it will return sum of try of Boolean, and try might be success or failure, and failure with exception. And because and because we handle this error, we can just assume whenever we get that value, it will be a sum of success of a Boolean. And if the value is not ready yet, it would be none. But it is not very useful, because if you are using future, it means that you don't know when the value would be ready. You want that computation to be executed in the background. So, but in case if you would like now to get the value, the result, you can wait for that result, and you can put the time, and this time should be like, you should be safe, that you should be sure that the delete profile will not take more than 1 second. So this is like the timeout. Otherwise, it will throw the exception of a timeout exception. Now we see how we can get started with futures. But now let's see which kind of challenges that we can face in concurrent applications. So in general, to make our applications useful, we want to have, like, for example, the useful applications that we can think of that handle many requests at the same time, and maybe like for example, an application to book a train or something like this. One of the applications that I will take an example for this application was that, and I faced a problem that was tricky. It was a program for an elevator system that has 2 parallel tasks. One that takes care of, that the elevators are moving, whether up or down each elevator, and handle requests will handle the request and look up for which elevator can can serve that request and update that state. There is a state in between these two parallel computations. So the program would seem like this. It has a variable, a shared variable, elevators, which contains the elevator state, and the elevator state has the current floor and the next stops. So, for the request, it's for the passenger, the current floor of the passenger and the destination. This example of the elevators is like when you are in like a modern building. There are modern elevators that you have to put your destination before you get picked up. It will, after you put your destination, it will suggest to you which elevator that will pick you up. And this is why it also makes it easier to like specify the destination, so you can check which elevator that can serve it. So here move elevators takes duration because it's the elevator will move between the floor, each floor every n period of time, like how long it takes to go from floor to another. And handle requests will return a future of unit, and run will combine make move elevators and handle requests running in parallel. So the tricky situation was that there was, to simplify, let's say 2 elevators, and the first one was in the 3rd floor going up to the 6th, and the elevator 2 was in the 10th floor going down. There was a request in the fourth floor going up, so the convenient elevator would be the first elevator. So the passenger will be waiting, and then suddenly there was something wrong, like the elevators were moving and it jumped. It sounds like it jumped because it moved to the 5th floor without picking up this customer, and the handle request already took supposed to take that elevator. This kind of problems really make the customers angry, and also doesn't like, imagine everything works, imagine your program, the test is working, and then they tell you, please, there is a customer is not happy, you should make sure. You will spend the whole day, why this doesn't work, in why? And like, you try to investigate and you cannot find the problem because it's very tricky to find the reason, and the devil really is in the mutable state in concurrent programs. It's not easy to reproduce the errors sometimes, and like, this is due to race conditions. And honestly, every time when there is a bug, I think it is a race condition. Even then, I found out that it wasn't even concurrent, because I really like, yeah, race conditions really are, it's a special condition that may occur inside a very critical section in the code, and you have to figure out where is this critical sections. So the thing that we need to understand is that how the threads going through and the state is going through the memory, the JVM memory. So here, every core is connecting, trying to update the main memory, because every thread will store its local state in registers and the local the cached memory, and then it will store it in the main memory, so the other threads in different cores can take this new value and load it from this main memory and use it and update it, and then store it again to the main memory. This is what is happening, but because executing the load and store in memory is done in order to exchange the information between the caches. And also it's very important to know that stores takes more time and is more expensive than loads. So to see the problem and the reason why this problem appeared in our program, it was first of all because of a visibility problem. The handler request, it was trying to get the current state from the main memory, and the current state was the right one, was like in the move elevator. It is the same one. After it takes, at that point in time, after it takes this current state, the move elevator has been moved. The elevator moved it up, and handler request didn't see that. It continued with the old state, and then it updates that state, and both of them were updating the main memory. And at that, in our case, the move elevator won that and put its state in the main memory. So the state was wrong, and the passenger couldn't find out where to go and whether the request has been failed or not. The customer didn't get any feedback. So how could we solve the visibility problem and the synchronization problem? If we had only the visibility problem, it would be solved only by just make the var volatile, adding this keyword. But for the synchronization problem, it is you need to be more you need to be expert to see where is the critical section in the code to make it synchronized, and where to lock the code, the instructions, and how could you use semaphores, etc. But fortunately in Scala there is actors. Actors are working very well with futures. In actor, you can define your mutable state, and then you can send to the actor to update the state or load the current state, etc. But using futures, it is not convenient for like sometimes when I currently I'm using futures and actors, but sometimes we need to be aware of things in future to not make mistakes. For example, that's like when we define a val that takes computation running in a future. For example, here, this will be executed right away. And sometimes, well, like when I started using futures, I thought that my program was sequentially, like here, after making sure that the user exists, I will do all of these things. And but here it's already done. Once you call the future, it will be running. And this is like we should be aware of. And if we want to define this, you can just do it as using lazy val. So it will be executed only when you call them here and not here. So when you call them in the flat map, it would be sequentially running. It will remove the user and then pictures and then education. And but here you might get an exception because the user is not found, and because this is not like this check is was returned false. And yeah, so this is we should be aware of this. And also that in case, for example, you would like to get the result from a future using a wait result. For example, here the future takes 2 seconds, more than 2 seconds, and then print out a message. And then when you were waiting for the result, you wait only 1 second. So the expectation is to have timeout exception, which is right. But after, when you look to the logs, you can see that that message was displayed, which means even you think that you have an exception, the future was running in the background. So even the program crashed, your computation was right, was done. Sometimes you think that, oh, there is an error somewhere, and you think that the computation didn't happen, but you found out that it happened. So this is just to be aware of. And also when you would like to have to check which future has been completed first, even though normally the second future, this future will finish before the future one, but you will see both of them were running. They will still running in the background, and you will get the correct result. So all of these things we need to be aware of. But also it is not only in future, even if we are working with threads, it is difficult to cancel or to stop the running, the execution of running tasks. So it is not something, yeah, it is something that we just need to be aware of. And this is why I would like also to introduce to you a library called ZIO. It is also encourage people to the users to write more functional programming code, even if sometimes, like for example, I am not a functional programmer person, but like I came from a Java background, but when you try to figure out why should I use something like functional programming, what would will help us, it helps us to reason about the code in a correct way. For example, if you see you can control your code and you can test your code easier than having everything out of control, like for example future. But even though future is quite functional program style, with when we are using composability in futures, it gives us power and many nice things, but a good advantage on ZIO that we can cancel the computations that are running in a fiber, because in ZIO futures are fibers, because there is a data type called for a normal program that is just a simple program. You can describe it in a data type called ZIO, which has 3 type parameters. It sounds quite a lot, but this, for example, the R is, when you look to the type signature, you can see the R, knowing the R is which dependencies your program requires. The E is which kind of error your program might fail, and the A is the result of the program. So, and all of this, because it encourages more to use functional programming. So this is only a description. It is just an immutable data type that to be able to describe your program there. And when you have, when you run this description, it will be executed in a fiber. For example, when in a normal program, when you run, for example, the main method, you say it is running in the main thread. For ZIO, it is running in the main fiber. And the fiber will hold the running IO value. And in case if we want to execute different concurrent, concurrent computations, we can make them running in different fibers. How could we do this? For a description of a normal program, you can see here, we have just a program that say print line hello, and we try to wrap it into a ZIO. This data, ZIO any nothing unit. It means that this doesn't have any dependencies, it will never fail, and it will produce a result of type unit, because print line, it will return unit. This, when you run the code, it will not be executed, only when you decide. This is what I mean about controlling your code. You decide when you would like to run this print line. And for a fiber, you can, for example, you would like to run this program in a different fiber concurrently. This, using .fork, this will create a program, a description. When you see ZIO, it is a description of a program that doesn't require any dependency, will never fail, and will be executed in a separate fiber than the current one. So this is, and a fiber here, it is, you can see it as a thread, but it is a lightweight thread. And you can have many fibers running in one single thread. So, also ZIO doesn't, like when you define the vals here and use them here, it doesn't change the meaning of the program. You can call directly them here or here, it's the same. It doesn't, the problem that we saw earlier with futures, it changed the meaning of the program. If you do a val future here and call them here, with future, the program will be parallel. But here, when we call them here and use them here, it would be the same meaning as calling them directly. Because every time when we call them, it is only a description of them. And when we want to use them using flat map and map, the flat map will take that ZIO and give the result of the first one, for example. The first program here, it will return the first one, and then the second computation will take, it will wait for the first computation, because flat map uses it's sequentially. So every time when you see this step, it will okay, delete user, it is a ZIO. It will take the result and put it in a D1, and then go to the next one and wait until the delete picture to give you back a result, and put it in D2. And this is the same meaning here and there. So, and also if you would like to get the result from the fiber, you can just call join. And if you have a timeout, you'd like to define a timeout, you can also, there is many different functions in ZIO. You can call .timeout, but actually I didn't want to dive deep into this topic because it is the main goal is to show how could we solve the concurrency challenge that we faced with elevator system using ZIO. But here I wanted to show that we can also interrupt the computation that was running concurrently. This is also awesome. It's yeah. And then now let's see. In ZIO there are many things, many data types, many functions that we can use on the ZIO data type that I showed you earlier. But ZIO STM is the data type that we need for our challenge. It gives us the ability to atomically perform a bunch of reads and writes to the transactional memory when a set of conditions is satisfied. The transactional memory here, we can see it as our state. So the STM data type describes the transaction that might fail with an error or succeed with a value of type A. The TREF holds the state. The A is our mutable state. So this is a description of the transactional memory that will be read and written inside the transaction. So when you see TREF, it is our transactional memory. So we can also see transactional reference. How ZIO STM works, in the beginning, it puts an initial state to our transactional reference. Then once, for example, when we start our transaction, we want to read the value from the transactional reference and then, for example, update it. And then if there is another fiber is using this transactional reference, this will automatically roll back to the initial state and automatically retries, waiting until making sure that no other fiber is using this transactional reference. This will guarantee the consistency in our program. And also we can put in our transaction, we can put a condition, and if it is not satisfied, it will retry and back to the initial state. In case if after we update the transactional reference and there is a failure, it will also roll back the whole transaction and back to the initial state and complete with failure. If everything works perfectly and afterwards we commit this transaction, we will build an a ZIO data type, which is a description of a program that contains the final state, which we will be very confident about it, and we complete this transaction. We will see this in detail with this example. So now instead of defining this var, we have our transaction reference of type of this state, the elevator states. So here, when we move the elevators, we need a clock. Here, when you see ZIO clock, nothing, okay. The first one is the dependency. This program, you can see, this is a description of a program that requires a clock. It will never fail and returns a result of type unit. So this clock, where it comes, it is from ZIO. There is a ZIO clock here, which will give us the ability to move the elevator on each duration and schedule the action. We will see this implementation, and handle events will require anything, will never fail, and it will return a unit. And run will combine both of move elevators and handle requests and combine them to be and ensure that they are running together. So move elevators task. It has the, it updates the elevator. Here, elevators is the transaction reference. It has update function that gives us the old state, and we can use this old state in order to compute the new state. And here we return the new state. This function will check whether this elevator is going up, following the upcoming stops, or going down, etc. And then we commit this transaction and we repeat it every duration. And all of these combinator are built on ZIO. This repeat will repeat this action in case of success, and this will always succeed. And it will repeat every point in time. And this is why when we call repeat schedule at this duration, this program will require the clock automatically. It comes from here. And handle requests takes the request from the queue, and it will look up which elevator that is convenient for this request. In case if there is no elevator, it will try here modify. It is not like update. It gives us the old state and updated here, but it will return the result in the right value here in the tuple. So now, in case if there is no available elevator, this transaction will retry. If there is an elevator, we will update the state. We add the stops of the current floor of the request and the destination, and we will succeed here. And all of this will return the second the left value of the tuple. And this is why here flatten, because it returns an STM, and this would be STM of STM. Flatten will make it just a single STM, and then we will commit this transaction, and we want to process the requests forever. And run will run both of them in parallel. So using here, this combinator is built on ZIO. It will internally use fibers to make sure to run both of these actions in parallel, and then return both of their values. And in this case, they will never finish because both of them are running forever. So let's see now, after this solution, what will happen. Handle request will check the current state. It will take that state. Now, when the elevator wanted to move, it will, as you remember here, if I mentioned it, when the transaction find out that another fiber is updating or using that transaction reference, it will retry automatically until there is no fiber is using this transaction reference. So currently, the move elevator will not be able to update the state. So here, the handle request will update the state with the current customer, with the current passenger, and then the passenger will be happy. The elevator one is waiting for you, and this elevator will pick them up. So later, afterwards, the move elevators will synchronize, will take the current state, which was already updated in the main memory. It will go up, update the state, and then update the main memory and go and move again. So now we solved this problem without focusing more about whether which critical section in the code that we need to log or something. No, we focus it only on the business logic, and we solved this concurrency challenge by choosing the right data type built on ZIO. I know concurrency is complicated and tricky, but it is useful to provide responsive and fast applications, and we can do it. So if you feel it was interesting to take a look on ZIO STM, you can check out the library, the ZIO library. And if you also would like to check out futures and how could we use the state using aka actor, here is documentation, and you can check out this library. And if you also are interested to see how functional programming libraries in Scala, like Katz effects and Monix, how they work, you can also check them out. Thank you for your attention, and I hope that you enjoyed, and I hope that you get inspired to try Scala. And if you are interested, you can follow me on Twitter and check out my GitHub for elevator system project if you are interested about the code.
Well, that was a really great talk. It's Mag here, just filling in for Barry. It's obviously a really complex topic, and I thought you brought a very cheerful way of communicating it to us all. I really liked your presentation, and obviously I think from your lovely accent that English is not your first language. So I think it's incredible, having spent the day trying to learn Spanish verbs, that you have the capability of expressing such a complex topic in not your first language. So really well done on that. And obviously you're very passionate about it, and it was really informative. And I enjoyed the real life scenario about the elevator. Like, for me, theory is hard to grasp, but when you put it in terms of me getting an elevator, I can get it.
Thank you.
And I think the audience was really engaged as well. We have a few questions. I messaged you directly in chat just so if you're comfortable with reading them, but I can call them out to you. So we have a question from, and pardon me if I mispronounce anybody's name, and feel free to tell me how to pronounce it correctly, because I would like to honor that. So from Rohitash, is there still context switches in thread pools? Was his question, and that was from the first quarter of the meeting, from the early on section. And feel free to jump in with details for whoever has asked those questions.
Okay. I tried to find the question about the thread. Is it from Jane or Rohit?
It was from Rohitash. It was the one, if you look at the chat that I sent you directly, it's the top question there. So is there still context switches in thread pools? And then there was a comment made on that topic that the only benefit I can see is that the control in spawning number of threads in the thread pool.
Okay, now
And I don't think we have Rohitash with us anymore to provide more details on that. We can come back to it if you'd like to jump to the next question. It might be more obvious. So from Mustafa, what is the benefit to define it as lazy in the delete profiles function?
Sometimes, because in the example that I have mentioned, there are futures that will delete accounts for a user, and afterwards there is a check if the user exists already, and then we will perform all of them sequentially. But once when we define the future as a val, they will be executed right away, and the application will fail because it executes right away. And when we make it lazy, it will be call it only when we call it inside the for comprehension after that condition.
Yeah, I think you might have mentioned that in your talk, and Mustafa might have been just ahead of you explaining that. So that's great. And then from Lalit, can ZIO be used in ACA, if I'm pronouncing it correctly, ecosystems? And so go ahead with that part.
Okay. I think I personally use it ACA ecosystem, and I wish to include ZIO. And then I found it is possible because there are there is a ZIO interops module, like a project in ZIO. It's not in the same repository, but there is ZIO cats ZIO interops or something that will switch to future. The last time I used it, it was a long time, and I'm not sure if it is available there or actually this is. But when I wished to use ZIO using in ACA ecosystem, it sounded quite complicated, but currently I'm using ACA ecosystem separately, and a new service using ZIO 100%. So I didn't have that experience.
Okay, well, it is literally impossible as a developer to keep up with hardly anything because things are ferociously so changing, and the interdependencies, it's madness. So we definitely can't be experts on everything. As a follow-on question from Lalit, sorry, and is there any benchmarking done yet? How does ZIO perform with respect to features?
I'm not sure about benchmarking, but I remember like it is just what I remember about some like I saw a presentation that presented some like comparison about ZIO and futures, and it says that ZIO is more performant, but I don't have like I cannot say it by myself. The only thing that I can say is that comparing to future, ZIO has you can use many fibers in using less resources than a future.
Okay, and Lalit obviously was very passionate about the topic and asked, can we use separate thread pools for specific fibers? Seems like a very detailed question.
I'm trying to, can we, separate thread pools for specific, you mean if we use specific thread pool in a fiber, or I didn't understand it well?
I can't give you more context, unfortunately. Can we use separate thread pools for specific fibers is all I have.
Maybe, yeah, I think maybe.
What I want was, can we separate the different thread pools for our different processes? Like I want to isolate my user processing with my like order processing. Like I don't want to, like I have bulk orders. I want to have a thread pool with maximum workers there and like lesser workers in the user processing. So
and using ZIO, right?
Huh?
Using ZIO, right?
Yeah.
Yeah, we can do this. There is a method called on ZIO that you can specify which execution context that you want your fiber to be executing.
Okay, does it use that Scala's global execution context, or like, or it takes
the default one, you mean, or?
Yeah. Yes, the default.
No, it doesn't use the default one of the global execution. It doesn't use it. Uses something that makes fibers lightweight, more lightweight than futures and threads.
Thanks.
Great, Lalit, I hadn't seen you there. You were behind my chat window, so I'm delighted you could give context more than me. As you can see, I have no idea what I'm talking about with regard to Scala or ZIO, but enjoyed nonetheless. So George, who is still with us as well, is there a Java version of ZIO, or is it only available in Scala?
I think there is not a Java version of ZIO, but it sounds interesting. But I feel like it would be cool if you try to use it in Scala. I don't know if there are also, because there are some projects, if your project is already using Java libraries, you can include Scala's programs. But I think I tried this in the opposite way. I have a Scala project and I use a Java projects, but I didn't try the other way around.
Okay, great. I think we've gone through all of the questions, and I think that was really excellent to have so many people here. Actually, it was a really great turnout, so obviously an interesting topic, and to have such engagement from everybody, I think that was a great sign of your talk. So personally, thanks, and I'm sure thanks on behalf of everybody else. So I'll leave it up to you to close the meeting with regard to your final comments or whatever you'd like to say.
I'm very happy to have this opportunity, and I'm happy that I see all of you, the attendees, and thanks a lot to join in, and yeah. And I hope really that the outcome of this talk, that someone at least would be interested to try Scala and to join the community, and yeah, this is
great. Great. And there's lots of thanks, and it's an interesting topic and a really nice presentation, great talk, lots of nice comments coming in. So well done. And I think you deserve to celebrate a good talk. So thank you very much, and lovely to meet you. And have a nice evening, everybody, as well.
Thanks a lot.
Okay. Thanks a lot. Good night.
Good night.